All right, we're back. This is page 1 of notes 11 of Calc C, and we're kind of moving a little beyond series here, or at least like delving into some other stuff. I think it's good to review some integrals right now and kind of like get back in the flow of that because you probably haven't thought about it. So what we're going to talk about is more types of trig integrals, meaning you've done u substitutions, which is kind of sort of what this is. You've done u substitutions in the past, and you've like recognized things, but let's do like slightly more advanced things, a little weirder. They don't really come up in Calc AB. I don't know how much they come up in Calc BC, but like you can't do Calc 3 if you don't know these kind of tips and tricks. So let's see if we can do this. These are a review, hopefully. So in my mind, you can do this one of two ways. You can like just do it, right? So I mean, I'm thinking, so I'm gonna write what I'm thinking. U is cosine of 2x. So there should be the derivative of that is well, I guess I'll just do the work. Negative 2 sine of 2x dx. All right, so I need a negative 2 on the inside, negative 1/2. And then you're going to get a 1/4 by reversing the power rule. You get cosine to the 4th of 2x plus c. So this is a straight u substitution problem. Not bad. You have to like recognize what to do, but I mean, hopefully at this point in your life, you're like, yeah, the thing to the highest power is probably u, and just go for it. Probably could have done that in your head. If you did, awesome. If not, it doesn't matter. You got the answer. Here. All right. So when you're dealing with this, you have to kind of like ask yourself, if I make u equal secant, the derivative of secant is secant tan. That works. If I make u equal tangent, the derivative of tangent is secant squared. So that works. So you can actually do this either way, I guess. So let's say option 1 is going to be u equals secant of t over 3. Right? So then the derivative is 1/3 secant tan. So you need a 1/3, so a 3. This will give us 3, and then reverse power rule. 1/3 secant cubed of t over 3 plus c. So we just get normal secant cubed. Normal secant cubed, as if that's a normal thing. Plus c. Option 2. So this kind of illustrates an issue that you run into a lot, in particular with trig functions, where there's often more than one way to do it, and then the thing that links them together is like the Pythagorean identities and plus c. And we have to contend with that a lot, especially when we're using a calculator to check things. So the derivative of, I probably should have written u equals. The derivative of tangent is secant squared, so it would have been 1/3 secant. So you're going to pick up another 3 because you need a 1/3, and then you get 1/2 of tangent squared of t over 3. So this, I think, is not working. Well, I don't know. So I'm getting 3/2 tan squared. I don't know where I'm going to like rectify that. Oh, wait, the derivative of, no, secant is secant tan. And then the derivative of tangent is secant squared. And I'm messing something up, but I don't know what. Or maybe I'm not. I mean, I'm pretty confident that I am. I got this. These are definitely not equivalent. So what did I mess up? Plus 1. So there should have been a 1/3 and a 3. No, okay. I'm looking over here. 1/3 and a 3. Sure, makes sense. The derivative of secant is secant tan. So 1/3 and a 3, and then you get 1/3. Yeah, I mean, I feel like that. Oh, no. Gosh. All right, u is equal to secant, but because du, oh, I did it to myself by not showing the work. Frustration, right? Du is 1/3 secant tan. And so because of that, it's not actually secant squared that you're integrating. You're integrating secant. So you get 1/2 secant squared 3/2. Oh God, it must be so frustrating to watch. Okay, so we get that. Now, why are these the same? These are the same because tangent squared of t over 3 plus 1 equals secant squared of t over 3. So you could replace the tan squared, or well, you could replace secant squared with, so this, replace it with tan squared plus 1. Then you'll have 3/2 times 1, but 3/2 times 1 plus c is just a new c. So these are actually equivalent because of that Pythagorean identity. Let's take a look at, I don't know, the next one. So that was bad. Show your work, people. Demonstration of the failure to show work right there. Also a demonstration, I guess, of the power of checking your answers and doing things in multiple ways. I don't really know. That's just me trying to excuse it. This, I think I'm going to go with, this is cosine of x over sine. And then if you integrate that, you're going to get the natural log of the absolute value of sine of x plus c. Okay, so I mean, that definitely works. The other thing, there's another weird way you can do this. I think it's kind of weird. I mean, it's not really that weird. You can, so you can take cotan of x and then multiply by cosecant over cosecant. And then the, like, y. Well, that's a clever form of 1, like a really clever form of 1. And then now, if we integrate this, we would get negative natural log of the absolute value of cosecant of x plus c. And then the -1 that's a coefficient becomes the exponent. This is equivalent to the natural log of the absolute value of sine of x plus c. So that's like another way to do it. It just, whichever one strikes you, right? For me, the cotan to immediately a trig identity works for me, but you know, do it however it makes sense to you. All right, there's gonna be another one where like you could, I can think of 3 ways to do this, unfortunately. So option 1, let's try not to get them wrong. U is gonna be sine of 5x, which means that, so du is 5, so this will give us 1/5 and then 1/2 sine squared of 5x plus c, so 1/10 sine squared of 5x plus c. That's option 1. Option 2 is, I mean, like, we're gonna like u equal cosine of 5x, which like I would pretty much never choose on my own because it introduces negative signs and like, so then du is -5 sine of 5x, so we need a -1/5, but then we just get 1/2 cosine squared of 5x plus c, -1/10 cosine squared of 5x plus c. So it's not like really obvious that these are equal, unless you're thinking sine squared plus cosine squared equals 1. So sine squared of 5x plus cosine squared of 5x equals 1. And since that's the case, we can just have the feeling that I hadn't hit record, but I did, which is like good and bad, because if I hadn't, I would go back and do B correctly and then like not subject people to that, but whatever. Anyway, you could replace sine with 1 minus cosine. The minus cosine is what turns this into a negative. You could replace cosine, no, sine over here with, what am I even saying? Well, you could replace sine squared with 1 minus cosine squared, or cosine squared with 1 minus sine squared. I don't remember what order I went in, but that's why like they differ by a negative. I think that conveys it. Option 3 is the weirdest one, but also I think the optimal solution here. So option 3, we're gonna use, oh, no room here. Use sine of 2a, like the formula for that, right? So sine of 2a is 2 sine a cosine a. So this integral is actually 1/2 the integral of the sine of 10x. So then there should be a 10, so a 1/10, so 1/20th, and then cosine of 10x, and then negative. Killing it. or getting killed by it, one of those. Now, like, why are these equivalent? These are equivalent because the double angle formulas for cosine, right? So, and we're actually going to talk about that in I guess the next video, because I didn't go through these that smoothly. So yeah, next video we'll talk about why all these are equivalent, but it has to do with the cosine of 2x. And there's 3 ways you can write that. So maybe go review that, or maybe you already remember, who knows. But anyway, I'm gonna end this video here, come back in the next one, finish this page. So I will see you there.